Our next topic is electromagnetic induction. Okay, so in the previous chapter we learned that if we place a current carrying conductor, so here is a conductor, assume that a current I is going up. Okay, if we place a current carrying conductor in a magnetic field, here magnetic field B is going into the screen. Okay, it will experience a force. That force, we learned that force F equal to BIL sine theta. B is the magnetic field, I is the current, L is length of the conductor, and theta is angle between B and I. Now in this chapter we want to see if we have force and magnetic field and L length conductor. If we have all these three, I mean we are providing the force in a magnetic field with L length conductor, can we get this current? Okay, that's what we're going to see in this chapter. All these experiments taken place around 1800, 1820, 1830s, around that time. So around that time there are two important, around 1830s, American scientist American scientist Joseph Henry and English scientist Michael Faraday, they were doing experiments to see how can we get this current, in a current carrying conductor. So Michael Faraday first published a publication paper based on this topic, so we call this as Faraday's law. So Michael Faraday started doing experiment. He took a electromagnetic material. Okay, here is electromagnetic material. Now he had two coils. Coil 1 is connected to a battery. Coil 2 is connected to a galvanometer. Okay, galvanometer is nothing but it's a voltmeter. Olden days it's a analog voltmeter. So here is 0. So if you go this side, 1 volt, 2 volt, 3 volt, something like this, -1, -2, -3. Okay, and here is a needle. Needle is always in the middle. Okay, so Michael Faraday started doing this experiment. So he thought that, see, he can create current in the second coil by connecting a source to the primary coil. Okay, so he thought that, okay, this will produce a magnetic field. This magnetic field is going to link to the second coil, and then he can see the voltage across the second coil. I mean, he failed so many times. We'll know in a few minutes why. But whenever, so I didn't put the switch here. So here is a switch. Whenever he's closing the switch, opening switch, that's where he saw a deflection in the needle. So I mean, whenever we are closing, it is moving one direction. Whenever he's opening, it is moving in another direction. So based on this experiment, he found that for sure we can produce, okay, current. Produce in the sense, I mean, remember one thing, we cannot create energy, we cannot destroy energy. That's a basic rule. So when we're producing energy or producing current, that means we're converting one form of energy into another form. So that's called induction. Okay, I'll talk about induction in one more time on another place. Okay, now I'll come back to the Faraday's law in a few minutes. Now let me find out how a current is going to pass through this conductor. So here is a magnetic field. Magnetic field is going into the board or going into the screen. Okay, that is B. Now here is a L length conductor. The length of this conductor is L length conductor. Okay. So this is a conductor. This conductor is already has lots of free electrons. It's moving around inside the conductor. The net displacement is zero, so there is no current passing through this, but there are thousands of millions of free electrons available here. Now I'm going to apply some force on this conductor, move this conductor in this direction, so it is velocity. Okay, I'm applying some velocity on this conductor. I'm moving it. So by using right hand rule, if you remember right hand rule, thumb indicates the force, middle finger indicates the magnetic field, forefinger indicates the velocity. So thumb indicates the force, middle finger indicates the magnetic field, forefinger indicates the velocity. Place them 90 degrees apart. Place them 90 degrees apart. So when we place them 90 degrees to each other, B indicates the magnetic, the middle finger indicates the, place middle finger going into the screen, and forefinger indicates the velocity. Now you can see this is going to experience a force towards up. Okay, so the conductor is going to experience sorry, not the conductor, the electrons, inside the electrons, because conductor is moving in one direction. So what happens here, the force on the electrons is going to appear on this electrons inside this conductor. So when electrons are going to move in one direction, I'm taking this electrons towards down because those are negative charge. A positive charge is going to be here. So whenever you have a positive charge separated by a negative charge, automatically there is an electric field between these two charges. Okay, whenever you have electric field, that electric field is nothing but you will end up having an voltage. So this voltage E, I'm representing induced EMF. I will talk about what is EMF and voltage in a minute. So this is induced EMF. So once you have EMF, which is nothing but voltage, now if I connect this conductor to a circuit, there will be a current passing through this circuit. Okay, so what is an EMF? EMF is nothing but electromotive force. Electromotive force. Electromotive force is nothing but whenever another form of energy is converting into electrical, we call that as EMF. So if you look at here, I'm applying force. So basically the kinetic energy. I'm moving this conductor in one direction, so I'm applying kinetic energy. That kinetic energy is converted into electrical. We call that as the induced voltage. We call that as EMF. Okay, battery converts chemical energy into electrical energy. There is also, it is called EMF. Okay, I think I told you this many times. EMF and voltage. Say for example, if I connect a 1.5 ohm across a 1.5 volt battery, okay, this 1.5 volt is the, assume that that's a EMF, induced EMF. Now what happens, there should be 1 ampere current passing through this. I equal to V over R, 1.5 by 1.5, this is 1 ampere. But in reality that current is going to be little less than 1 ampere. What happened there is some internal resistance, some variable internal resistance inside that battery. Okay, even though this voltage is 1.5 volt, there might be only say 1.4 volt is going to appear across the terminals. We call that as the terminal voltage or voltage available, because there is a voltage drop across this resistor of 0.1 volt. Okay, so the current passing through this is I equal to 1.4 divided by 1.5. This current is 0.933 amperes. Okay, 0.933 ampere. Now instead of 1.5 ohm, now if I connect a 0.15 ohm resistor, okay, now what happened, if I don't have an internal resistance, then it's supposed to supply 10 ampere. But in reality, this current is only, I mean, these batteries can supply around 1.5, 2 amperes. Assume it is 2 amperes. Okay, so basically what we see, this is a variable resistor, internal resistance. So basically what we see here, all we can see is 0.3 volt across the load, and the remaining 1.2 volt will drop across the battery inside across the internal resistance of that battery. Okay, so there is a huge amount of heat produced inside this battery. Anyway, our goal is what is EMF. I want you to know what is EMF and what is voltage. Here, this 1.5 volt is called EMF, electromotive force, because the chemical energy is converting into electrical inside this battery. Now this 0.3 volt is called voltage, because that's the voltage available across those two terminals. So that's the difference between EMF and voltage. Now another topic I want to talk about, induction and conduction. Induction and conduction. Whatever we saw so far, always current pass through a circuit because of the conduction. Conduction is nothing but there is a direct physical connection or physical link. Connection. So here in this circuit, say there is a current of 1 ampere passing through this circuit. So here 1.5 ohm, I'm going to talk about theoretically. For sure there is 1 ampere current passing through this. So in this circuit, current is passing through the circuit because of the conduction, because a physical connection, a closed circuit between the resistor and battery. When it comes to the induction means inducing. I mean, something is far away and current is passing through that circuit. So in the previous case, you have a magnetic material. Okay, these two, coil 1, coil 2, there is no electrical connection, these two, because of the current flowing in first coil and EMF induced in the second coil, that's called induction. Induction is nothing but there is no electrical connection, but still current is produced in the second coil because of the current flowing in another coil, or that's another reason. I mean, another way of saying this is induction is nothing but current is produced in a magnetic field by applying force. That force is nothing but moving that conductor. That's called induction. That's the difference between conduction and induction. Now coming back to our previous example, so as long as you keep if we apply a force on a conductor in a magnetic field, it will produce an EMF, that induced EMF E equal to BLV, where V is the velocity, okay, L is the length of the conductor, B is the magnetic field. Okay, so now we saw that as long as if you keep a current carry, if you move a current carry, as long as if you move a conductor in a magnetic field, it will produce an EMF. Now if you connect that conductor to some load, that will be a current passing through it. Thank you.